Okay, so introduction version of a phasor. Okay, you got two sources in phase. Okay, and there's some sine function that gives you the phase, right? Well, let's just assume the sine function is amplitude or well, it's going to be some a times the sine of omega t. Okay?
So they have the same phase and amplitude?
Yeah. Yeah, implicitly same phase. And I said they're in phase. I didn't say same amplitude, but yeah. Okay? Just like you got a plane wave coming in here and you got two slits. These two slits are going to be in phase sources with the same amplitude, assuming you have a plane wave whose intensity doesn't vary much, at least between here and here. Okay? And since the slits are likely to be very close together, well, that's kind of going to be it. Okay? Okay, so path difference is a sine theta. And we've drawn that picture. If you don't remember the picture, look up two slits in your book or anywhere, and you'll see the same picture everybody else uses. Okay? Path difference is a sine theta. So the phase difference is, well, if a sine theta is a wavelength, then you have 360 degrees of phase difference, right? Or 2 pi radians of phase difference. Of course, we'll use the 2 pi. Make sense? And this is just because you do a sine function, right? And then you do a sine function one wavelength later. It's going to just trace the same path in the same graph. Okay, so phase difference is, I'm going to just say 2 pi times a sine theta over lambda. Okay? Now lambda is just a wavelength. Okay? It doesn't really matter what the wavelength is, but it's going to be related to omega and to the propagation velocity, right? And to determine what's happening to the intensity at this point, or to the way the two waves combine at this point, it doesn't really matter what the propagation velocity is. Okay? Okay, so there's your phase difference, 2 pi times a sine theta over lambda.
What is A in this case?
Separation of the two sources.
Okay.
This is a detector, which could just be a screen that shows you how bright the thing is, right? If it's a light wave, like we saw, with the laser and the crude diffraction rating. Okay. Okay, so it follows then at the detector. The detector. At the detector, you have an a sine omega t and a sine omega t plus phi, or if you want minus phi. Okay? Well, you combine those and you do a little trigonometry and you get the amplitude of the combined wave. Okay? Now, without doing the trigonometry, we can visualize that on a circular model. Something I've been trying to get you to think in terms of, which I think is some pretty good success, since September. Okay? Because they're important. We did it with simple harmonic motion because I knew it's going to be so important throughout the course. Not just because simple harmonic motion is, because any such oscillatory function is. Okay? And when you drive the RLC circuit with an oscillatory EMF, well, you get what you get. And we'll talk about that later. This is a baby introduction to the idea. And it's very simple now. Here, I'm using the sine function. And that's okay. Yeah, I'll just keep using it. Usually when I use a sine, I regret it because I like to use the cosine to project down onto this axis. Okay, but it doesn't matter. Okay, so what we have now is we have okay, the y-coordinate here and the y-coordinate here are a sine of omega t and a sine of omega t plus phi. Of course, we know that adding phi shifts everything in the direction, in the negative direction, okay? So it's just our angle in the negative direction. So in here is our angle phi, right? Okay? So the net vector that represents this expression is the sum of these two vectors, right? So we take these two vectors and find the resultant just using the parallelogram method. Okay? And the magnitude of this projected onto the y-axis gives you the magnitude of the combined functions. Okay? Now there's some flaws with the model I'm using here, but I just wanted to show you that you can do this analytically using your sum of angles formulas. Okay? You can do it geometrically with triangles. Okay? Law of cosines might be a good thing. But it all comes out the same. So we'll do more with it next time.